So this is the first of my mini lectures on section 6.1 on definitions of linear transformation and helping you to understand linear transformations and what we do with them. So what I'm going to start out with is I'm going to start out with this notion of a mapping, or the definition of a mapping. A mapping, and we'll call this T, from a vector space V to a vector space W, is represented as T, V to W, and takes elements in V and relates them to elements in W. In the case of our mappings, V is called the domain of T, and W is called the codomain of T. Now, I'm just going to talk about this a little bit abstractly. So what I'm going to do is I'm going to draw a little picture. So what I'm going to have here, this thing here, this is going to be V, that's going to be my domain. And here's W, that's my codomain. Okay, and T is this mapping, and it'll take an element, say V, a vector V, in V, and it'll take it to another vector W in W. Okay, and what we're going to do, one of the challenges that we're going to do is to start to define how exactly it is that that T takes V to W, right? What kinds of V's can we take to W? What kinds of W's can we get back, right? Okay, in what ways do they make those relationships? And that's going to be what linear transformation is going to be about. A lot of it's going to be very similar to the work that we do in linear algebra, but from a different context. It's like the context of function, and you may have seen these relation pictures in the context of function. Okay, so that's our first idea of mapping. Now, what we want to talk about then is a linear transformation. Okay, our next definition, a linear transformation is a mapping from T to W, from V, excuse me, V to W, and we'll call that mapping T, such that, and we have two properties that we have to have. One, for all V1 and V2 belonging to V, belonging to V, T of V1 plus V2 will equal T of V1 plus T of V2. Okay, and so that's the addition. It's called closure under addition. And so that's my first one. And my second one, well, you can probably guess, it's going to be closure under scalar multiplication. For all V belonging to V, T of V, T of SV, and, excuse me, S, right, belonging to, and in truth, we're generally going to utilize another name for basically another space, but let's make it S belonging to R in this case for our purposes. T of SV will equal S times T of V. Okay. All right. And so that's closure under scalar multiplication. It's very similar to what we did with subspaces. Now, the difference here is, first, is to notice that what we're saying is that if I act upon, or if I utilize my transformation on V1 plus V2, it's like using the transformation on V1 first, and the transformation on V2 first, and then adding after the fact. Okay? So it's not really like the same in terms of like they belong to the space. It's not a set theory kind of idea. Instead, it's this idea of I can either add and then transform, or I can transform and then add. I can do it in either order. And the same thing with scalar multiplication. I can either scalar multiply, right, and then transform, or I can transform and then scalar multiply. I could do it in either order, although we still call it closure. All right, so it's just a different kind of concept, right? So what kinds of things end up being linear transformations? Oh, well, actually, let's first talk about a little bit conceptually. So again, I've got V, okay, and I've got W, okay? So what that means is, like, if I take V1, and I know that V1 goes to W1, okay? And I have V2, and I know that V2 goes to W2, right? Then I know that V1 plus V2 is going to go to W1 plus W2. And that's addition. These are all under T, right? It's addition. Or, if I have, in scalar multiplication terms, if I have V and I have W, and I take T, okay, and I have V1, and I have V1 goes to W1, and I have SV1 is then going to go to SW1. And that's the idea of a linear mapping, okay? All right. So, what kinds of things? Let's take an example of a linear transformation, okay? And so, we're going to say the matrix A, and this is any matrix A, is a linear transformation. And we're going to get more involved into this in a little bit, but let's just take and let's prove it. So we'll let, and this is how we write it, let T, and let's say it Rn to Rm be the linear transformation A, be the matrix A. Okay, so if I take a vector, and then we'll let V1 and V2 belong to V. A, the matrix A, times V1 plus V2 is going to equal AV1 plus AV2. All right? And by the way, this is T of V1 plus V2. That's how we write it. The transformation means that I act upon V1 plus V2 with A. Then, utilizing just rules of matrix multiplication and addition, I get that back, and this is then equal to T of V1 plus T of V2. Check. That's closure under addition. Then, if we say let V1 belong to V and S belong to R, T of SV1 is going to equal A times SV1, which is going to then just equal, well, if you remember about scalar multiples, the scalar multiplication, it's just going to, we get to pull it out to the other side, S times A V1, which is thus equal S times T of V1. Why is it that we can do something like that? Well, that's because A of V1 equals T of V1, right? By like definition. Same with A of V2 equaling T of V2 by definition, right? So basically what we're doing is we're showing that essentially we end up with distribute, okay, the v1 and v2 across the linear transformation, and that's the thing that allows us to get the t of v1 plus t of v2. And the same thing with the scalar multiple, right? It basically allows us to have commutativity this time with the scalar multiple, to move it out to the front side, okay? And so matrix multiplication is a linear transformation. It is a Lin transformation. There you go. All right. Well, so we've got, all right, that's a cool example. Now let's take a look, and we're going to look at a corollary. And this one states that a linear transformation, a transformation is a linear transformation if and only if and only if t of v1, or t of c v1 plus c1 v1 plus c2 v2 is equal to c of t of v1 plus c2, so c1, c2 t of v2. Okay. Now notice this is an if and only if. I'll rewrite it. If and only if. So that means it's both ways. Right? So first, we'll do some proof work, because I think this proof is handy. Suppose t is a linear transformation. By closure under addition, closure under multiplication, we can do this. T of c1 v1 plus c2 v2 is equal to t of c1 v1 plus t of c2 v2, which by closure under scalar multiplication is c1 t of v1 plus c2 t of v2, right? So just using closure under addition and closure under multiplication, we end up getting the equality that we want. Now, that's one way. Next, suppose that t c1 v1 plus c2 v2 is equal to c1 t of v1 plus c2 t of v2. Okay. Now first, we want to show that t of v1 plus v2 equals equals t of v1 plus t of v2. Okay. So let c1 equal c2 equal 1. Then t of v1 plus v2, okay, is, or t of c1 plus v1 plus c2 v2 is equal to t of v1 plus v2, which, because t is a linear transformation, is going to be t of v1 plus t of v2, which will end up equaling c1 t of v1 plus c2 t of v2. Now, so there's your there's your equality, right? Okay, we end up with, here's addition, proven. All right. Now what about scalar multiplication? So for scalar multiplication, we want to show ST of V1 will equal, T of SV1 will equal ST of V1. All right, so, and this is the second part, we're going to let T of SV1, okay, equal T of SV1 plus 0V2, okay, which will equal, by our same equation, right, by the fact that we have this, will give us ST of V1 plus 0T of V2, which will just equal ST of V1. And we have check, scalar multiplication is done. I'm going to go back, actually. I'm going to redo this one. Because what I did was I assumed what I was trying to prove. So just really quickly, it won't take long. We're going to take T of V1 plus V2, and that'll equal T of 1 times V1 plus 1 times V2. That's assuming letting C1 and C2 equal 1. Then this is going to equal 1 T of V1 plus 1 T of V2 because of this statement, this true statement right there, okay, for all C1 and C2, and that'll equal then T of V1 plus T of V2. And now we've proven addition. So T is a linear transformation. All right, that's cool. I like that. It's nice. Okay. So this is like our shorthand way of proving that something actually is a linear transformation. Instead of proving addition and multiplication, we could prove addition and multiplication all at once. So let's take another example. Here's another example. And this example is let T, and we're going to go from, it's called C1 on an interval I. Okay, so C1I is all of the first order derivatives, okay, all functions with first order derivatives, to C0I, which is basically all functions, okay? So we're going to take that as a transformation, and we're going to let T be, so T of V1 is going to equal just F prime of X, so it's the derivative. We're going to take the derivative, okay? Not V1, we should say T of F of X is going to equal just the derivative, okay? So T of, and we'll take C1 F of X plus C2 F of X, or C2, that's F1 of X and F2 of X. So we've got two different functions multiplied by a scalar. This is going to then equal, well, if we take the derivative, it's going to be C1 F1 of X plus C2 F2 of X. We're going to take the derivative of that. Okay, there's that derivative. Okay? Now, if you take the derivative, we kind of know a couple things. Well, first, let's take the derivative of each function. And so across addition, it's just exactly what we expect. It's going to be C1 F1 of X prime plus C2 F2 of X prime. Okay, and that, we know that that's true because you could just take the derivative across addition. Then we're going to then take the derivative here. Well, you know, that's just a constant times the function. So that's going to be C1 F prime of X, F1 prime of X, excuse me, plus C2 F2 prime of x. Okay? Which, shockingly enough, is t of f1 of x, or excuse me, it is c1 t f1 of x plus c2 t of f2 of x. And so the derivative is a linear transformation. How cool is that? And it turns out, although I don't know if we'll get to this, it turns out that you can actually form matrices that will, in fact, take the derivative of functions. So we can take the derivative of functions utilizing matrices, which is kind of a cool little result. Okay? So those are our big results for this first part of 6.1. The defining of a linear transformation, proving that something's a linear transformation, and then giving us a sense of what a mapping is.